Hey guys, happy week 3. I know that last week was a lot. Polar equations are definitely tough. So just be mindful of that this week. We are going to continue talking about polar equations. Specifically this week, we're looking at graphing polar equations. And while it's a little bit challenging, I think it's super interesting. The graphs that you're going to make this week are so cool. They're so pretty and fascinating, and it's really interesting that we can mathematically represent these like beautiful patterns as an equation. So we're going to look at how to do that this week and how to turn those equations into these really cool looking graphs. So you want to make sure that you just feel comfortable with those polar coordinates last week. Feeling comfortable with the fact that the x coordinate represents our r value and the y coordinate represents our theta value. If you were okay with really the graphing part of it, then that's okay. That's what I really needed you to feel comfortable with last week, is how to plot a polar coordinate. If you can do that, then you're going to be okay for this week. And then hopefully we can keep working with those polar equations to make them make a little bit more sense as we move forward. So with that, let us jump over to our notes. Okay, so zoom that in a little bit so it's a little bit closer. Okay, so we are on page 32 today, symmetry and polar equations. So you'll find that when you do these types of things, if you were to graph every single point on these equations, it could take a while, right? To get these completed figures, like in algebra, if you graphed a line, you could graph 2 points on a line and then you have the line because you know it's going to be this figure that goes straight like this. Polar equations make these, like I said, fascinating things. You'll see things that kind of look like, hold on, let me pull this up again. Okay, you're going to see things that kind of look like this. Like this is one of the types of graphs that we're going to graph, is a shape that does this. And they'd call this a 3-petal rose. And I didn't do a very good job of it. But you're going to create that mathematically in an equation and then graph that. Things that might look like this, for example, which is called a spiraled limacon. Again, terrible drawing. Terrible. They look better in my notes, but drawing on this pad's a little bit tough, especially because it makes it super bold right there. So if you're okay with the graphing part to it, like I said, we'll keep practicing the equations and make a little bit more sense of them as we move on. But this week's idea is to graph them. And like I said, symmetry, we're going to graph parts of it. We're going to look at parts of it and then use symmetry to figure out what the rest of it looks like. So couple things that we have to think about. The polar equation can be symmetrical in 3 types of ways. The first way is being symmetrical over the line theta equals pi over 2. So remember, theta equals pi over 2 is like 90 degrees on our unit circle. So that's that line going right up and down, or the y-axis. So being symmetrical over the theta equals pi over 2 is the same thing as being symmetrical over the y-axis. Meaning if you were to take a coordinate plane and reflect this side to this side, they would be the identical exact same things, right? The second one is over the polar axis. Remember, the polar axis we said last week was like the x-axis. So basically, I reflected something from the top 2 quadrants and reflected it down. It would be the same thing. And our third type of symmetry that we might look for is being reflective over the pole, which would be like being reflective over the origin in algebra, right? You know how sometimes if you took something and you could reflect it from quadrant 1 to quadrant 3 and they were the same diagonally, which essentially is the same thing as reflecting over the y-axis and then reflecting over the x-axis. It's doing both of them. So if it can reflect over both of them, then it's reflecting over the pole or reflecting over the origin in a rectangular plane. And like I said, this is kind of some examples of what you're going to see. And like I said, they look way better when I drew them in my book. So this first one shows a representation of being reflective over, or symmetrical over the theta equals pi over 2. You can see that the left and the right side of that first graph of this one right here are identical to each other, right? If I were to draw a line through here, the thing on the left side and the thing on the right side are identical to each other. Same thing over here, the polar axis. If I were to draw a line right here, this petal and this petal would reflect onto each other, and this part right here would reflect onto this part right here. So they are symmetrical over the polar axis. And like I said, the last one is the pole. If you were to take this piece and reflect it through this diagonal line, that piece would be the exact same as that piece. So those would be your 3 symmetries that you're looking for. So in order to prove this, we have a couple little formulas. Each one has 2 formulas that you have to test to make sure that it is or is not actually symmetrical. If it doesn't work with one, you have to try it with the other. And then if it doesn't work with both of them, then you know it doesn't work at all. That said, if one of them works, it is symmetrical. You don't have to try both of them if one of them does work. So if we want to test if it's reflective over the theta, reflective over theta equals pi over 2, you can do one of two things. One, you could change the radius to negative and also change theta to negative. If you do those two things and then solve the equation and get the same exact equation, you know that it is symmetrical over theta equals pi over 2. Similarly, we could also use changing theta into pi minus theta and then simplifying it. If you get the same equation, then it works. In the polar, you could keep r the same, but then replace the theta as a negative and simplify and see if it works. Or you could change the radius to negative and then replace theta with pi minus theta. And last is over on the pole. To check the pole, you would make the radius negative and leave theta as theta and simplify. Or you could leave the radius as the radius, but then you can plug in theta plus pi and see what happens. There are a couple things from our previous notes that might be beneficial here. There was a couple of formulas back when we did our trig identities that we didn't really use. They're the even odd identities. Even odd. And so the even odd identities just say this. If you have the sine of negative theta, that is equal to the negative sine of theta. If you have the cosine of negative theta, that's just equal to regular positive cosine of theta. The negative doesn't affect it. And if you have tangent of negative theta, that will be equal to negative tangent of theta, very similar to the sine of theta. So what that really means is that the sine and the tangent functions are odd functions, but your cosine function is an even function. And that represents also the reciprocal functions. So cosecant is the reciprocal of sine, so cosecant of negative theta would equal negative cosecant. Secant is the reciprocal of cosine, so the secant of negative theta is equal to positive secant of theta. So they follow their reciprocals. The other two formulas that are really important are your sum and difference of sine and cosine formulas. You're going to need those again. So you'll want to remember that the sine of a plus or minus b is equal to sine of a cosine of b plus or minus cosine of a sine of b. What did I just click? Oops. Sine of b. And the cosine of a plus or minus b is equal to cosine a cosine b, the opposite sign, so minus plus, and then sine of a sine of b. So write those down. Make sure you have those because you're going to want those to be doing these problems. It's going to make doing these a little bit easier. Okay, let me figure out how to select that because I need that to go away now. Go away. Be gone. Ah! Oh, no. Oh, no, don't do that. Undo, undo. Okay, you know what we're going to do? That's a terrible... Oh, wait. Let me just do this. Let me get the eraser. I'm learning still. One day this will all make sense. I don't want that eraser. Stop making fun of me. I know what I'm doing. I'm not a boomer. Okay. There we go. There we go. There we go. I should have written them on the side. I don't know what I was thinking. That would have just made all that easier. Okay. So as we navigate down this way, let's take a look. I believe that we just have one example, and I've got my selecting off there. I have just one example. So actually, let me just flip over here then. I wasted all that time. As always, I'll put that example up at the end in my nice writing. But for now, let's take a look over here. Okay, so it says determine the types of symmetry for r equals 3 plus 2 cosine of theta. So for now, and for your first homework assignment, I really do just want you to work through all of them. Because as you practice it, you're going to become more comfortable with it. And you're going to become more accustomed to what you're doing. But as you go through them, you're going to start picking up on certain patterns that happen. And that's okay. If you pick up on those patterns, you can apply those patterns. And you'll see that in my future notes, I do apply those patterns because there's certain things that I recognize that I'm not going to sit and test all three types of symmetry every single time. Because there's certain ones you're going to start looking at and be like, oh, I know which type of symmetry is that because it has this type of function. Okay. So for now, like I said, go through the first homework assignment and just do them because it'll make a little bit more sense that way. All right. So if I want to test r equals 3 plus 2 cosine of theta, the first thing I'm going to check is across theta equals pi over 2. And so remember when we did that, there were a couple things. We said first, for theta equals pi over 2, we could replace negative r and negative theta. And if you get the same equation, then you know it is symmetrical over that line. So I would just change r to negative r in this original equation up here, we've got equals 3 plus 2 cosine of negative theta. Well, we just talked about this. Since cosine of negative theta, it's just equal to its regular version, right? Cosine of negative theta is equal to cosine of theta. So we could rewrite this as 3 plus 2 cosine of theta. Well, I got to solve for r again, so I'm going to divide everything by this -1. And what I end up with is that r is equal to negative 3 minus 2 cosine of theta. That is not the same as the original formula, so I know that this would be a no. It is not symmetrical. But like I said, you have to test the other version as well. And so the other version was to take that formula, and in this case for the theta equals pi over 2, it says leave r the same, but replace theta with pi minus theta. So we end up with 3 plus 2 cosine of pi minus theta. This is where we're going to have to jump in and use that sum and difference formulas for these ones. So I end up with 3 plus 2, and then in this parentheses, we're going to take this cosine of pi minus theta and plug it in as a formula. Remember, the cosine of anything plus or minus is cosine of a and b minus plus sine of a and b. So we're going to do cosine of pi, cosine of theta, and then since I had a minus sign up here, we're going to put a plus sign here. And then we're going to have sine of pi and sine of theta. And then I'm going to do my best to simplify what I can over there. So I have r equals 3 plus 2. Well, I know the cosine at pi. Well, let's think, because we're going to need pi in just a second. So if I'm thinking about my unit circle, I know pi is over here. That's going to be the coordinate -1, 0. So that tells me that the cosine is -1, 0, and the sine is 0. So cosine of pi is going to be -1. And then I have cosine of theta, which I can't solve because theta is a variable. And then I have sine of pi, which we just said is 0. So I've got 0 times sine of theta. Well, pretty easy to simplify this. 0 times sine of theta is still 0. It doesn't matter what sine of theta is. We know it's 0. So I end up with r is equal to 3 plus, distribute that 2 in, we got -2 cosine of theta. Still not the same as the original, because now I have a -2 cosine of theta instead of +2. So we'd say no again. And ultimately from this, I could deduce that it is not symmetrical over theta equals pi halves or the y-axis. So we're going to jump in now and we're going to try to do the other two. I'm going to go ahead and clear that out. Okay. So now we got to test over the polar axis. So polar axis, the first thing that we check is we replace r with r, so that's going to stay the same. And we replace theta with negative theta. So we're going to end up with r equals 3 plus 2 cosine of negative theta. Again, we've already determined cosine of negative theta is equal to cosine of theta. So r equals 3 plus 2 cosine of theta. That's the simplest I can get it. And look at that. That formula and that formula are identical. So yes, these are symmetrical. Now, at this point, if you wanted to, you could test the second one just to verify. You could go ahead and plug in negative r equals, and then 3 plus 2 cosine, and we replace that with pi minus theta. And you could work that out if you want to, but ultimately you're going to get a yes again, because that's how it works. Like I said, if it works for one, you don't have to test the other one. All right. Clearing that out, then, we know it is over the polar axis. So actually, let's go ahead and write that up here in a different color. So we're going to put polar. It is symmetrical over the polar axis. Okay. So the last one, let's test if it's symmetrical over the pole, which we actually have a really good idea of this already, right? If it's symmetrical over the pole, I lied. Ignore me. No. I was going to say something and I realized I was about to say that's not right. Okay, so let's actually do this then. So we're going to replace these ones, the negative r, and theta stays theta. So it's going to be negative r equals 3 plus 2 cosine of theta. Well, not really much we can do except divide by the -1, right? So we're going to end up with negative 3 minus 2 cosine of theta. That is not the same, so we're going to put a no right there. Okay, let's try the other side of that. 3 plus 2 cosine, and we're going to replace theta with pi plus theta. I forgot to put r equals. There we go, sorry. So r equals 3 plus 2, and then we're going to do our formula again. So I've got cosine of pi, cosine of theta, And since it's a plus up here, remember cosine switches. Sine stays the same, but cosine switches. So we're going to change the sign and put sine of pi, sine of theta. Okay. Well, we've already done this once. We know this is -1. We know this is 0. So ultimately what that tells me is we're going to have 2 times negative cosine of theta, and then this 0 doesn't matter, right? At that point, I already know enough to say. When I distribute this in, I'm going to have -2 cosine of theta, and I should have had +2 cosine of theta. So this is still a no, meaning that overall in this example, it is only symmetrical on the polar axis. That's it. So you got one axis of symmetry. So let me put my notes up again so you can see those all done nicely. I say nicely, but I did run out of room a little bit here. Okay, so there is the example that we just did. So you could take a look at that, write that down, make sure that you got all that. And that's where I'm going to stop. So that first homework assignment is just really going through and doing that. I know it's a little bit tedious, but it's going to kind of get you those skills as you start understanding which ones have symmetry over which lines, and you will be set. All right, talk to y'all later. Bye.